Welcome back, and again let us do another numerical problem, engineering mechanics problem set 2.6, solution to 2.90. So in 2.6 we have been using method of moments, that is the turning effect of a force about a point, for which we need a perpendicular distance from the point to the line of action of the force, and the force multiplied by that perpendicular distance give a turning effect about the point of contact. It can be either clockwise or anti-clockwise. Now look, a bracket ACB, this is a bracket. It can slide freely on a vertical shaft BC, but it is held by a small collar attached to the shaft S. This is a small collar attached to the end C. This is a small collar attached to the end B. So it is holding it and it is not sliding down. There is no friction also. Neglect all friction. Find the reactions at B and C for the vertical load shown. Here is a vertical load 4450 Newton. The bracket should slide down, but due to the collars it is held in position, and there will be reaction force at C and will be also at B. That we have to find out. Now let RB is the reaction at B, RC is the reaction at C. Line of action, if I produce this line downward and the reaction here, RB to this side, they will meet at this point, and let that point is equal to D. Now the question is, your RB is to this side and this vertical load 4450 Newton is to this side. So the resultant of these two will be pointing to this side. So to balance it, there must be another force pointing in this side. And what is that? That will be the reaction. So the reaction force, if you call this point D, the reaction at C must pass through the point D and pointing in the direction DC. That I will show in a different diagram. So the line of action of 4450 Newton and the reaction B, when produced, they meet at point D. Now therefore the conclusion is, therefore RC must point along DC, from D to C. The reaction force at C must point that way. Now let us take the moment of the force about point C. Sum of the moments. Now the diagram is redrawn for you. Now let me explain the diagram. This part is this part, this part is this part, this part is this part, and this part is this part. Means here is point B and here is point B. This part is this part, this part is this part, this part is this part, this part is this part. Means point C is here and point B is here. So let us begin. So let us take the moment about point C. The direction of RB from point C is at this perpendicular distance. That is given as 350.6 millimeter. So RB times 350.6 millimeter is a anti-clockwise movement about point C. And what is the perpendicular distance of this vertical load? This vertical load from the point C is at this perpendicular distance. That is also given as 300.8 millimeter. So 4450 times 300.8. So if you cross multiply, your RB comes out to be this much. Put it in a calculator. This comes out to be 3817.9121 Newton. This is your one answer. Then Let me draw a perpendicular. Let me draw a perpendicular here on the line DC. This is 90 degree. So in the triangle BDE, which is right angled at E, your BD is the hypotenuse, EB is the perpendicular, and ED is the base if you consider this as angle as alpha. So let us take tan alpha. So tan alpha will be this perpendicular. So tan alpha will be 350. If you can consider here also. No, I will find it later on. We don't require it. Now, if you join it here, this is also 90 degree here. So your tan alpha will be this distance BC over BD. And from B to C is given as 350.6 millimeter. From here to here, which is shown here in the scale, is 350.6 millimeter, and this distance from B to D, this distance is same thing as 300.8 millimeter. So in triangle DBC, which is right angled at B, if you take tan alpha, it will be BC over BD. Put the value, so your alpha comes out to be 49 degree 22 minute 18.48 seconds of arc. Now we'll take the moment about the point B. Now about the point B. Now RB is passing through the point B. Means RB does not have a perpendicular distance from point B. So RB does not contribute any moment about point B. RB contributes 0 moment about B. But this force, 4450 Newton, the load, has this perpendicular distance from here to here, from point B. So 4450 Newton has a perpendicular distance from point B, that is this perpendicular distance, which is same thing as this distance, which is same thing as this length. So 4450 has a perpendicular distance 300.8 millimeter. We need to find the perpendicular distance of RC from point B. So therefore this perpendicular is drawn, BE is drawn. Now let BE is perpendicular drawn on DC. BE is perpendicular drawn on DC. Now if you take sin alpha, it will be this perpendicular by hypotenuse. So by cross multiplying, BE can be found out. So that will be the perpendicular distance which will be required to find the moment of the force RC about point B. RC will have this perpendicular distance BE from the point B. So let us take sin alpha. So sin alpha will be BE over BD. Don't look at this part. I wrongly took as tan alpha. So sin alpha is BE over BD. Sin alpha is BE over BD. BD's length is given as 300.8. So if you cross multiply, you get BE as BD sin alpha. So now let us take the moment of the load and the reaction force about the point B. So RC times BE will be 4450 Newton times BD. So that is what I have written. So RC times BE is 4450 times this. So take BE to the right hand side, and for BE substitute this value BD sin alpha, BD sin alpha. Now since BD is given, put this value here, and alpha has been calculated. So you put in a scientific calculator, this comes out to be 5863.35 Newton, the reaction force at C. So that is all about. I will upload in few minutes from now. If you like the videos and the explanations are convincing to you, don't hesitate to subscribe and give your comments if you like. Thank you.